building. Right now we are in Davidson Life Sciences. You go across the parking lot, go past the building, and then enter through this big space, and that's right across the street from the pharmacy building. Once you enter the building, there is a sign for the room, and we are in room 304. So make sure that you give yourself enough time to get to that building.
That room is real close to that entrance that we pointed out on the map. If you know forestry, it's really confusing. So that's the easiest way to get, the closest way to get to that room.
The other announcement is that we are going to have our review section for exam 2, and it will be today 4 to 5 p.m. In the room B116A, still in this building, but in the B tower. I am not going to give any lectures. I'll be there and answer any questions you may have. And for the exam, my best suggestion for you to prepare for it is that follow the study guide and go through all the slides. You don't need to spend too much time on the papers themselves. Just focus on the slide. Make sure that you understand most of the concept on the slides. You remember to bring your computer. You can bring your charger also for the exam. You need a lockdown browser. I have experience from exam 1, so you don't need to follow that. The last announcement is that the score for exam 1 is going to be available right after this class, and Dr. Vidal is going to make some announcements and introduce the statistics for exam 1. So at the end of this lecture, we'll have about 8 to 10 minutes. So Dr. Vidal can talk about exam 1. But you don't need to worry about that at the moment. Before you talk about that, let's go into our lecture today. And today, we are going to talk about complex trait and genome-wide association study. Do you still remember what we talked about last time? We talked about Mendelian disease. So what is Mendelian disease? How is it different from complex disease? Mendelian disease?
Are they normally one mutation caused by one gene mutation?
Yes. So Mendelian disease are relatively simple genetic disease. They are usually controlled by one gene. So if there's mutation in that gene, it is going to cause Mendelian disease. Sometimes it can be controlled by multiple genes, but there's one causal gene and other genes are just modified genes. What would be the traditional approach to find the genes that are responsible for Mendelian disease? What's the method we use to find the disease-causing gene?
Linkage analysis?
Yes, linkage analysis. And what kind of data do you need for linkage analysis?
Pedigrees?
Yes, pedigrees. Cool. So, can any one of you give me, for example, an example of Mendelian disease? Any kind of disease that belongs to the Mendelian disease category?
Cystic fibrosis.
Yes, cystic fibrosis. What kind of inheritance pattern?
It's an autosomal recessive disease.
Cool, that's right. It's autosomal recessive for cystic fibrosis. Another example?
Huntington's?
Yes, Huntington's. What's the inheritance mode?
Autosomal dominant.
Yeah, so it's actually the only example of autosomal dominant talk about in our lecture. What about complex disease or complex trait? Can you give me an example of complex disease? Complex disease? Too simple? Anyway. So what would be the major feature for complex trait?
Well, I was going to say that a trait could be high because it's like multiple genes affected, and it's not like one major effect, it's a bunch of little effects.
Yes. So most of the trait we notice right now, like height, weight, skin color, type 2 diabetes, cancer, heart disease. They are all complex traits that controlled by many genetic factors. They are also strongly influenced by environmental factors. So the having those genetic factors is not deterministic for disease, because you can modify your environment so that to decrease your disease risk. Today we're going to focus more on complex trait and talk about the research approach to identify genetic variations that are controlling our risk for complex disease. And this is what we go over last lecture about Mendelian disease and complex disease. And you need to understand the difference between those two categories. For Mendelian disease, the traditional approach, the old way to identify disease-causing gene is the linkage analysis using data from a family tree, or from family tree and pedigree. They are the same. The general approach with linkage analysis is that you usually start with one patient, usually an infant that has a severe genetic disease. We try to identify the cause of mutation, and then we collect data from the family. We build a pedigree tree. We collect the DNA sample and do some genotyping. And for linkage analysis, the number of genetic markers usually is fairly small, like about 800 is not many. Remember that in our genome, comparing the genome of any two people, the number of genetic variation is about 5 million. So 800 is really small. And then once you collect the genetic marker, the pedigree structure here, you can put those data into a statistical model. And usually we use LD score to measure the linkage between the marker and the disease. And so these are the successful, so for each marker you can calculate an LD score. So you do a chromosome Y or genome Y calculation, and you locate to a region that has very high LOD score. Do you still remember the cutoff? You try to find a significant LOD score. What's the cutoff? Usually when we do statistical tests, we use p-value less than 5%, right? The LOD score, what's the score? Yeah, it's 3. Usually when you have about 3, it gives you an indication that there's a strong linkage between that marker and the disease. So it's actually the linkage between that marker and the disease-causing mutation. For most of the mutations that are causing Mendelian disease, they usually have very low frequency. So here the x-axis indicates the frequency of the mutation. And for Mendelian disease, usually if a person have that mutation, there's a very high risk for the Mendelian mutation because they have a very strong effect. So it's also called highly penetrant. Highly penetrant is that for the individuals that carry mutation, there's a high probability that they're going to have that disease. So if you look across this panel, so at this corner are the mutations that are commonly causing Mendelian disease. They have been usually identified using linkage analysis. Looking at this corner, so these are the mutations or alleles that has high allele frequency, so they are commonly found in the population, but they have relatively small effect size. For those genetic variant, the genome-wide association or association analysis is more powerful to identify those kind of genetic variations. And look at the upper right corner. Those are the common variation, but also have very strong effect. For those genetic variation, for example, for the ApoE causing Alzheimer's disease, and CFH is a complement factor H, is causing aging-related macular degeneration. So for that kind of mutation that has very, very strong effect, it's just like the Mendelian mutations, but on the other hand, they're very common. For that kind of mutation, they could be identified using both approach, linkage or association analysis. Question?
What exactly are you talking about when you say effect size? Like, how do you measure that?
Great question. So effect size depends on what kind of trait we're talking about. For example, if we're talking about a specific disease like type 2 diabetes, if a mutation can increase your risk of type 2 diabetes, we can ask how much does that mutation increase the risk of type 2 diabetes. And usually for disease, the effect size is measured by odds ratio. So basically compared to the general population, to a specific person has a 1.5-fold increase in risk or 2-fold increase in risk. So that's one way to measure effect size for disease. When we talk about quantitative trait or continuous trait like height, so in this case, it's not we are using it's called how much you increase height by having a specific mutation. You increase by 1 centimeter if you have one copy of that mutation. If you have 2 copies, you increase 2 centimeters. So that's another. It's called beta. It's a beta from the linear regression statistical analysis. So it depends on what kind of trait you use. You have a different statistic to measure effect size. But here it's referring to both any kind of measure you use. So for the last lecture, we mainly focus on Mendelian disease and using linkage analysis to find mutations that are related to Mendelian disease. In this lecture, we're focusing on common variants that have small effect, that are play a more important role in complex disease. And the traditional linkage analysis is actually not very successful with complex disease, because for the traditional linkage analysis, you use pedigree data. Imagine that there's a common variation that is causing a specific disease like type 2 diabetes that's running in the family, but for some of the family members that have that mutation, because the effect size is small, if they live a healthy lifestyle, then in that case, although they have the mutation, they don't really have the disease. So in this case, linkage analysis doesn't really work. Population-based association analysis is the approach to identify that kind of genetic variation. And comparing linkage analysis, actually, I didn't emphasize it. The common disease, common variant hypothesis is that common diseases are likely influenced or caused by genetic variations that is also common in human population. And that was the original rationale for genome-wide association study. Is that for specific complex disease, the mutations that are causing that disease is quite common in the population. So many individuals will have that population. Although some of them don't have the disease, but because of a large number, we can still identify those mutations. Comparing linkage analysis and association analysis, linkage analysis using pedigree data, like members from an extended family, and those families are connected by a family tree. The association analysis recruit participants from the general population. Usually, you want them to be unrelated because basically you require them from a different family. But we know that all human individuals are connected in deep history. So although those individuals are unrelated, but in history, they are still related in some way. So those individuals are connected through a population tree. And for a case control, like for a genome-wide association study, for example, for specific disease like heart disease, you recruit patients that have disease and then you recruit control, basically healthy people. And then you look for a specific genetic marker. You test if the frequency is different between cases and controls. And that's the basic study design. So because of this study design, in this small family tree, the number of recombination events is relatively small. So the resolution is fairly low in pedigree analysis. For population analysis, because the history is much longer, there's a much longer time for recombination to happen, so it can break down the linkage between, it can break down LD blocks. A better way to visualize this process is that when you look at, so these are the pedigree, and think about that those are the chromosomes at the very beginning, and then recombination can break down the association between SNPs in different locations. And eventually, going through those recombination events, we go down to this segment. So in this segment, genetic variations are linked. They're in strong linkage disequilibrium. And this is the resolution linkage analysis can reach. It's at the order of megabase, usually like 20 megabase. And in that 20 megabase, there are a large number of genes, so it's really difficult to figure out which gene is the disease-causing gene.
In my intro genetics class, we mentioned the genetic studies of Icelandic people and the long genetic record that's been collected there. Would that be like an ideal population for a study such as this because they're isolated and homogeneous and have a long history of reported genetics?
Yes. Yes. So this is actually a great example. It's that kind of data is rare because in the Icelandic population, they have a very clear record of their pedigree, and also they have relatively good electronic health record. And about 10 years ago, there was a big genetic study in Iceland where they do sequencing or genotyping for most of the individuals in Iceland. And then they can put the data back into, so basically they can trace, they know the relationship between those individuals and they are related through many generations. So in that case, you have a big sample size. It's actually many families. And you know their relationship, you know the pedigree, so you have many recommendations in that family tree. So basically you have many more number of recommendations, and you have the very clear record of medical history. So you can actually, you have the advantage of the traditional linkage analysis, but with the added strength of the big data set. But that kind of data is really rare. And so compared to linkage analysis, with association analysis, we collect samples from unrelated individuals. But those individuals, we think about it in the initial, when we collect, so all the individuals can trace back to some common ancestor, right? And over time, there's many more recombination happen that break down those LD blocks. So you have a much higher resolution using association analysis. Usually it's at the level of kilobase. Now we know that the genome is organized into LD blocks. And for genetic variations that are in the same LD block, they are correlated. They carry the same kind of information. So we can imagine that we can just pick one genetic variation to represent all other genetic variations in that specific LD block. Using that idea, we go through the genome. You need to pick one SNP for each LD block, and that is going to significantly reduce the amount of genetic markers we need to include in our analysis. And this is the rationale for us to select genetic markers in genome-wide association study. And for each LD block, the extreme case is that you pick just one genetic variation to represent that LD block. But usually, to increase resolution and to increase power, you pick a few more genetic variations in each block. And the SNP that are chosen as marker, they are also called tag SNP. Basically, those SNP tag the other genetic variations in the genome. And in this case, for example, we look at this LD block. And this is the disease-causing SNP. But in the real study, we may not include this SNP in the study because we just pick one SNP as tag SNP. So genotype this SNP, we do the analysis, but this SNP is able to help us locate to this LD block. And so two different concepts. Direct association is the association between the causal SNP and the disease. The indirect association is the association between the tag SNP and the disease. And in genome-wide association analysis, when you we only include specific number of genetic markers. And so for most of the analysis, we don't really know if they are direct or indirect association. For example, if we have a SNP that is strongly associated with type 2 diabetes, we actually, based on looking at that association, we don't know if that SNP is causal or not. And we need molecular experiment to test the causal effect of that mutation. But we can be fairly confident to say that the majority of the association we found in a genome-wide association study, they are indirect associations. Okay, so the question is that we know that genetic variation are organized into LD block, but what is the pattern of LD block in the human genome? Once we know the pattern of LD block, then we can pick SNPs for each LD block. And this project, the International HelpMap project, was designed to study LD block patterns in the human genome. And so LD block sometimes is also called haplotype map. Basically, in the LD within a block, the number of haplotype is greatly reduced because loci close to each other are strongly linked with each other. And the International HelpMap project was started right after the Human Genome Project. It was started in about 2003. So the Human Genome built a reference genome for human. For this HelpMap project, it focused on specific mutations in the genome. It focused on about 3 million SNPs in the genome. So you just randomly choose some SNP in the genome, and then you determine the genotype for those SNP in about less than 100 individuals from different human population. And then in each population, you study how those SNP correlate with each other, and that's how you define LD block. The reason they are including different human population is that the LD block pattern are different across different human population because of different evolutionary history, and we're going to talk about that in a few slides. So in this study, they included about 207 individuals from 4 populations, look at about 3 million SNPs. And they actually in the European ancestry, in the African ancestry, they use trio data. So basically they have the child and they have the 2 parents. Because that was at the very early stage of studying human genetic variation. So having a trio data, because you can compare the genotype in the child to the genotype in the parents, and that can help them first increase the accuracy of the genotype code, and of course they can also study how genetic variation is transmitted from one generation to the second generation, and how recombination break down those associations. Just a side note, it's not important for you to understand at this context. And for the East Asian population, they use unrelated individuals. After the phase 1 and phase 2, so phase 1 and phase 2 only focus on 4 human population, and they found significant difference in terms of LD patterns. And so later in the phase 3, they extend to many more human population. And in this case, they reduce the number of SNP. One major reason is that you just want to save cost. The other reason is that based on the study of that 4 population, there is some common pattern that some SNPs are correlated with each other across all 4 populations. So in that case, you already know that it's likely that those SNPs are correlated with each other across many populations. So you don't need to include those SNPs. So you just remove some redundancy, so that can help you reduce the number. Question?
So I'm a little confused between the difference between the International HapMap project and the 1,000 Genomes project that we talked about earlier. It seems very similar.
It's very similar.
Yeah.
So, so the HapMap project was an earlier project. So
Okay.
the Human Genome Project finished in 2001, 2003. That's the Human Genome Project. Try to build a reference genome. Right after that, we figure out that okay, we know the genome, but still we don't know what the genome do, and especially we don't know the pattern across human population and how those genetic variations associate with each other. So the natural idea is that let's sequence the genome of more individuals. But in 2003, the second generation sequencing technology was not ready yet. Second generation sequencing technology was available in 2006 or 2007. So in that case, at that time, when you try to study genetic variation across individuals, you won't be able to sequence the whole genome. So the strategy is that let's focus on some specific site in the genome. So in this case, they pick they pick 4 million sites to study. And then eventually for about 1 million of the sites, either they have low quality or they turn out to be not polymorphic across individuals. So only about 3 million SNPs is different across individuals. And the technology they used was not sequencing. It was genotyping array. And I'm actually going to talk about genotyping array in a few slides. So they're using genotyping array at that time was relatively less expensive. And genotyping array is like based on the reference genome, you need to focus on specific sites in the genome. And because we have the reference genome, we know the sequence context of that specific site. So that, and we know that for that site, we know it is a SNP, it has 2 alleles. And we know the sequence context, we can design 2 probes, 2 oligonucleotides. One can hybrid with 1 allele. So you put those 2 probes into a chip, right? And then you have a new sample. You apply the target DNA, and the target DNA will bind to a specific oligonucleotide, and that can help you identify the genotype of the new DNA. And that is called genotyping array. It was relatively cheap at around 2003. It was not that cheap. Otherwise, they would include more here. And then in 2000, after the International HapMap project was finished about 2008, and because it was targeted at specific site, and after this project was finished, we realized that all those genetic variation we studied here are common variation. We didn't include rare variation. So the 1,000 Genome Project was designed to do whole genome sequencing so we can identify all possible genetic variations in the genome. And it was mainly driven by the technology we have at that specific time. So Human Reference Genome Project, and then the HapMap project, and then the 1,000 Genomes Project. So those are the 3 major projects to study human genetic variation. And in the HapMap project, one of the major purposes is to define this kind of LD block. And so we talked about this kind of figure last time. Here, basically, the chromosome is listed in the horizontal direction, and the triangle here indicates the level of association or the level of LD between any 2 SNPs. The red indicates that the 2 SNP is in strong LD. And basically in this block, indicate that all the SNP here is in strong LD with each other. And that is an LD block. And you can see that the LD block is relatively constant across different human populations. This is African, European, and East Asian. You can kind of see the same block. And those blocks are separated by recombination hotspot. We know that recombination is the major force to break down LD. One interesting thing to notice that is that you compare the color in the block is that the color is not as strong in the African population. And basically, the African population has a weaker LD. The LD block is smaller in African population. And actually, we can look at this figure. This figure using across the 22 chromosome and the sex chromosome, and different color represent the LD or the linkage between nearby genetic variations, and red indicate very strong linkage. And this is African, European, and East Asian. And if you look at that, compare all three of them, you can notice that first, the degree or the strength of linkage, this equilibrium, is different in different parts of the genome. Some genome has a stronger LD, some genome has a low LD. So blue indicate low level of linkage. And another major pattern is that the LD pattern is like LD block is much smaller or much less in the African population. And why? Why African population has a smaller LD block? And that is related to the history of the human population. So all modern humans originated in Africa, and then for this lineage is the migration out of Africa. So this lineage has East Asia, and then we have Europe, and then Asia, and then America and Australia. So basically, you can think about so these are all African populations. These are African populations. And if we think about African population, the tree for them is this part. And for the non-African populations, the tree for them is here. So the African individuals that connected through a much deeper history. So because they have a longer history, they have more time for recombination to happen. And recombination breaks down LD block. And that's why Africans has a much smaller LD block. And the smaller LD block indicate that, okay, so you have many more small LD block in the genome, then you need more tag SNP in order to tag those LD blocks. Overall, across the genome, you only need about 500,000 to a million SNP to capture the majority of the common variation in the genome. And for different population, you need different SNP because the LD block is different. And the African population need more tag SNP. And now that based on the HapMap study, you can, for example, based on the HapMap study, you can choose about 500,000 SNPs as your tag for genome-wide association analysis. And that's what researchers did. And once you choose those 500,000 SNPs, the question is how, like, you know which SNP you want, and then you recruit some human subject. The question is, how did you measure the genotype at those positions in those large number of individuals? And they're using the genotyping array, and this is the technology I mentioned for HapMap. And this is the same technology used in HapMap and the technology used in genome-wide association study. And the reason they're used is that they are fairly efficient and they are cost-effective. It's a very cost-effective way to measure the genotype for close to a million SNP. And there are two major technologies out there. The most popular one is the Affymetrix. It's just a chip with oligonucleotide attached to that chip. And for Illumina, they have a similar technology, but it's based on bead. But it's all based on the hybridization between the design oligonucleotide and the target DNA. So the important point here is that they are not sequencing. Maybe I think I will stop here and let's take a short break before. And the first kind is the case control study. And the case control study was the study designed for binary tree or for most of the disease. And basically you recruit a group of participants with a specific trait. For example, patients with a specific disease like heart disease. At the same time, you need to recruit another group of participants that don't have the trait, like healthy individuals without a specific disease. So this is called case control study design. And once you have the case control status, you genotype the genetic markers. And then for each genetic markers, you can test if there's a different frequency between case and control. And in this case, for example, for individuals that with the heart disease, they tend to have a C allele at this specific marker. The statistical method used in a case control study usually is a contingency table. For example, you can do a chi-square test for comparing people that have disease and without disease and look at what kind of alleles they carry. And this, we don't need to know the detail, but contingency table and logistic regression are the statistical methods we use to start to do an association analysis for case control study. And for each specific marker, the significance level is just regular 5%. Another major group design based on the for quantitative trait is also called continuous trait. For example, for height, for skin color, for weight, for your blood glucose level, for example, all those traits that is continuous. You won't be able to cut and separate into two groups. For that kind of trait, usually you use a linear regression study design. And this is a basic example of linear regression. The each dot represents one individual, one participant. And then for each participant, you know their phenotype. So this is the phenotypic value. It could be height, it could be glucose level, it could be lipid level. And then the x-axis represents the genotype. And this is just one specific way to indicate the genotype. So for each SNP, you have two alleles. And you can choose one allele as the allele under study. And then you can having 0 of that allele, 1 copy of that allele, and 2 copy of that allele. And see for individuals with different genotype, do they have a different phenotypic value? And this is a simple linear regression. And in this case, having one additional copy of the target allele increase your risk by increase your phenotypic value by about 1. If you have 2 copies, you increase the value like 1.5. It's not 1, it's like 0.8. So it's a linear increase based on how many copies of that allele you have. And the significance level is the same. As long as you're working on one genetic marker, you're looking at this significance level. But for genome-wide association analysis, we are really working on the genome-wide genetic markers. And this is a regular way to show genome-wide association result. This is called a Manhattan plot. And each dot represents one genetic marker. And so the x-axis represents the position of that genetic marker. So here's chromosome 1 to chromosome 22, the autosomes. And then the y-axis represents the statistical significance. And you need to know that it is represented at the scale of negative logarithm. So if you have a very, 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 very significant p-value, basically you mean you have a very, very small p-value, then after the transformation, you are going to have a very, very high score here. And this is a very effective way to visualize genetic markers that are significantly associated with a specific trait. And because this look like the landscape of the Manhattan Island, so that's why they call Manhattan Pond. And those are the cutoff. And because you are doing statistical tests for many genetic markers, and for each statistical test, we have a false positive rate. If we use a p-value of 5%, it's a very, very high false positive rate if we do that many tests. Usually, if you do many statistical tests, you need to further lower your significance level. And in GWAS, the significance level used is 5 multiplied by 10 to the negative 8. And that's the significance level used in most of the genome-wide association study. This is another way to visualize the GWAS result, and each dot represents one SNP. The x-axis represents the expected p-value. The y-axis represents the observed p-value. The idea is that if a trait is not controlled by genetic mutation, then no genetic variation is going to be associated with that trait. So all the association analysis, all the statistical tests we did, is going to give us a random p-value. In that case, we expect to observe the observed p-value fall along this line. But if there is a true association, if there's a genetic variation that causes increased disease risk, those mutations will have a much more significant p-value. And so looking at this kind of figure, usually a reliable QQ plot that tells us that we found something in the data is that you need to have, at the very beginning, the observed p-value follow the expectation, but at the end, there are some line that has much higher significance, indicating that those are the SNPs that has significant association with the trait we are studying. So those are two plots you can see in most of the GWAS paper. And for most of the statistical analysis, you need to control for some confounding factors. For example, gender, age, study site, ethnicity, and some other no clinical covariant. Controlling those covariants can increase your power to find the association between genetic factor and the disease. One of the important covariant is the population substructure. Basically, when you recruit individuals, you want to make sure that those individuals are from the same ancestry. Because, for example, you recruit Europeans or you recruit Africans. You don't want to mix people with different ancestry because that can create a very severe problem. It's a very severe confounding factor. You can so first we know that different human population has some difference in their genetic variation in terms of frequency because they have different evolutionary history. And imagine that one extreme example is that if there's a mutation, for example, in Africa, that help them adapt to the environment, so that mutation will have high frequency in Africa but low frequency in Europeans. And so those mutations, we call that we have many mutations that has different frequency in different populations. And then for some disease, they also tend to have different prevalence in different human populations. And in that case, when we recruit participants that has different ancestry, it's very likely that the mutation you found is just mutations that by random have different frequency in different populations. So that's why when you do a genome-wide association study, you need to make sure that your participant has a relatively close ancestry, not from very different ancestry.
How are populations like in Europe or maybe like the US where there's a lot of like movement from like location to location, how do they control for that? Like If you look at like Germany or something,
Yep.
and there's a lot of immigrants there, or like even immigrants from other parts of Western Europe because of the like freedom to travel. How do you control for that? Do they tend to look for people who have lived in the same place for a long time, like their family has lived in the same place, or does that not really matter?
So two responses. The first is if you are able to recruit individuals that has like their family live in a specific place for a long time, that's ideal. But even in that case, sometimes even for the participants themselves, they don't really know about their family history. Second, more commonly, we recruit participants based on some questionnaires, like roughly where your family is from. And the critical step to rule out or to remove the confounding factor is doing, after you get the DNA data from different participants, you can do analysis. Try to, basically you can view a phylogenetic tree and see how individuals are closely related to each other, and then there's going to be some outlier. And then you can do like a population, so you can do a population structure analysis, you can do PCA analysis, and after you plot them to the figure, you can clearly see that for individuals that are closely related, they cluster together, and there will be some outlier. So based on DNA data alone, you can tell them apart. And that's what traditionally do to remove people that with different ethnicity. And so now we have the study design, it's a very clear design. We have a fairly cost-effective approach to get genetic data. So what we need right now is that we just recruit participants. We genotype them, we measure their phenotype. Either the best way is to have their electronic health record. Imagine that you have a cohort of participants. You have their genetic data. Their genetic data only need to be measured once. And if you have their electronic health record, so you know their disease status for many diseases. You also have data for their many like biomarkers, glucose level, lipids. So for each one of those measures, you can treat them as a phenotype. And then you can perform a genome-wide association analysis with those phenotypes. So you can really, with one data set, you can make a lot of discoveries. And that was what researchers did starting about 2005. 2005 was the first year the first large-scale genome-wide association was done. And this is one of the biggest study. It was published in 2007. And in this specific cohort, they have about 17,000 individuals. And in this paper, they focus on 7 common diseases. And then for each one of them, you can perform a genome-wide association study, and that can help you locate to the genetic regions that are associated with specific disease. So these are the examples for disease, for binary trait. This is another example for quantitative trait, like cholesterol and then triglycerides. Those are continuous traits. You can do the same kind of analysis with a slightly different statistical method, just do linear regression. And in this case, they also found a lot of very strong association signals. So GWAS has been proved to be very powerful to help us identify genetic variations associated with disease. And all those, so for the last 15 years, a lot of genome-wide association study has been done. For example, even for the same kind of trait for type 2 diabetes, several research groups, they're going to go out and recruit their own sample. Like some research group in Europe, some research group in US, some research group in, for example, East Asia. They all do their own study of GWAS for type 2 diabetes. Now, when we have all those data, we can do a meta-analysis, try to integrate those data into one consistent data set. So we have a much bigger sample size. Just remember the control for the population structure because including people from different places. But even for European populations, you can have multiple studies, and you can integrate them through meta-analysis. So meta-analysis has been commonly used in statistical analysis. It is used to integrate, to infer significance effect size by integrating studies. But the studies need to be studying the same disease and same hypothesis. So that's the criteria. And for the statistical analysis, you don't even need the raw data. You don't need to know the genotype information or the disease information for the patient, for the participant. And those information usually are very sensitive. And research group, they usually don't release that kind of information for privacy reasons. And meta-analysis doesn't require raw data. They only need the summary result. When we say summary statistics, basically it is for each specific SNP, we know the significance of the effect. We know the effect size of that SNP, and we know the p-value of the association between that SNP and the disease. And the effect size is the summary statistics. And for meta-analysis, you only need those summary statistics. And another benefit is that meta-analysis increases the power to find association. The problem with meta-analysis is that when you try to integrate multiple different studies, like different study using different technology to genotype their genetic marker, using a different set of genetic markers. For example, some study using Affymetrix, some study using Illumina. And those two companies has different set of genetic markers in their technology. And when you try to merge those two studies, some SNP is present in one study, but not present in the other study. And that's caused a lot of problems. And one way to address that inconsistency is using genetic imputation. And in one of the previous lectures, I mentioned that genetic imputation is that, for example, if you, in your new data set, in one of the GWAS, you have a missing data in this location, you can, based on the LD pattern in the reference data, you can infer the genotype for those missing locus. And the commonly used reference data set right now is the HapMap and the 1000 Genomes Project. So we talked about the two data sets before. And the 1000 Genomes Project is the preferred reference because the 1000 Genomes Project has theoretically all the genetic variation in the human population. So using 1000 genome population, you can really, like, when we start with, for each genotyping array, usually you have about 500 to 1 million genetic markers. After imputation with the 1000 Genomes Project, you can get information for 80 million genetic markers. So this is just another workflow for genetic imputation. These are the reference data set.
So the assumption is that if you find a certain SNP with one study and then a different SNP with the other study, if they're close enough together, you can say they're basically accounting for the same genetic variation. Is that how you can infer?
No. The idea is that, so for example, this is one study. So we are for this specific study, we have a missing data here. And then imagine that you have another study, you have a missing data here. So when you try to merge the two studies, this SNP is missing in this data set, but this SNP is missing in the other data set, right? So you won't, in this case, you could not merge information for those two SNP. And what you need to do is that you can do imputation separately for two data sets. For the first data set, you do imputation for this SNP. For the other data set, you do imputation for this SNP, so that in both data sets, at the beginning, they all start with two SNP. Now, they all have three SNP. So in that case, you can easily merge the three SNP.
And the imputation is possible because the SNPs, the known SNPs, are close enough to the unknown SNPs?
Yes. Yes.
Okay.
So imputation relies on the LD information between nearby SNPs. And you need to have a reference panel. And that reference panel, like this one, has many known haplotypes. And that kind of haplotype give us information to infer missing data in the new data set. So that's the reference data set. If you have a new data set, basically what you are trying to do is try to build the haplotype, like for that individuals. And then once you build the haplotype, you can compare to the reference gene, the reference data set, and then to fill in the missing places. And so it's really doing haplotype phasing when you're trying to do genetic imputation. This, I just want to give you another example of the power of genome-wide association study. This study focused on fetal hemoglobin level and also beta thalassemia. And so the fetal hemoglobin play an important role to alleviate the symptom in this specific disease. And previously, so in this specific study, you actually integrate both linkage analysis and genome-wide association study. And remember that for the linkage analysis, you need to have pedigree data. And they were able to locate to this specific genomic region that has one very strong association signal. So we go through the whole genome, 22 chromosomes, you found this region that has a strong linkage to the specific trait. And then you do an association analysis. In this case, you use unrelated individuals, and you help you locate to three major places. And just pay attention that for one of the specific location on chromosome 11, it's actually the same location. So linkage analysis and genome-wide association analysis in this case are able to locate the same gene. And this gene is it's called HBB. It's hemoglobin unit B. It's one of the major. It's beta unit for hemoglobin proteins, and it's already known to play an important role in the level of hemoglobin. Additionally, they identify population association analysis is much more powerful, and they were able to identify a few more association signals, especially at this position, BCL11A. And this is the association analysis with imputation. So with imputation, you get many more genetic markers. You borrow information from your reference dataset. So you're actually able to get a much stronger signal here. And the idea is that with many more markers, you get closer to the disease-causing mutation. And once you get closer to disease-causing mutation, the association signal will be stronger. And that's another benefit of genetic imputation. And then if you zoom in to this specific region, you identify that, okay, you find at least 2 SNPs that has very strong association signal in this region, and you locate in this specific gene. And if you look at the association of the genotype and the hemoglobin F level, there is a significant association between them. So this is a classic study to identify through genome association analysis and help you locate a candidate gene and find a candidate mutation. A lot of studies have been done since 2005, and the GWAS results are collected in this database. It's called GWAS catalog, and those are the location of the significant association with different disease. And right now, it is over 700,000 associations has already been found. A huge number of them. This is just the legend, not really important. The point here is that if you're interested in a specific disease, for example, if you're interested in a specific trait, like blue versus green eye or some specific disease, you can go to the database, you put the trait, you can search what kind of genetic variation is associated with that trait. You can search by specific disease, like cancer, what mutation is associated with cancer. You can search by genomic regions. In each specific region, how many traits has been associated with this region. So genome-wide association analysis in the last 15 years has really revolutionized our understanding of complex disease. And now genome-wide association study was mainly using common genetic variation. And now the new wave of study is mainly to couple genome-wide association analysis with sequencing data. And hopefully that can increase our understanding of complex disease from the perspective of rare genetic variation. And the last note is that this lecture is going to be covered in example, so remember to study this lecture. That's it, and questions?
How are like I guess popular sites and programs like Ancestry.com or like 23andMe changing how these studies are performed or like public opinion about these studies?